Hi class, in this lecture here we want to talk about finding limits both graphically and numerically. So in the first lecture that you would have watched about this, I talked about something called the limit process. So what you did was you looked at the value of x, or in those first videos, delta x goes to some value. In those videos it was like as it goes to 0. So I want to introduce limits kind of with an example where you're looking at a function. Okay, so here's this. Let's consider this function. F of x is equal to x squared minus 9 divided by x minus 3. All right, so the first thing I want to do is I want to find what is f of 3, okay? So if you were to do this, right, what you would do is you would plug 3 in for x, and look what happens. You get 9 minus 9 over 3 minus 3. This is wild. You get 0 over 0. Well, we know we cannot divide by 0. All right, so this is bad. But actually in calculus, when you get this to something that looks like 0 over 0, it's what's called indeterminate form. And well, in terms of just the function, this is undefined. You can't have this, okay? But it turns out when you have this indeterminate form, the 0 over 0, you're going to be able to evaluate a limit, okay? And now let me show you something. So now that we know that f of 3 is undefined, okay, let's sketch the graph of this function. Well, so here's the thing. If you were to look at this, you can see that this is the difference of two squares. It's going to factor into x minus 3 times x plus 3 all over x minus 3. Well, look, these terms will cancel out. And the graph of this function is just going to look like x plus 3. But we know x cannot be equal to 3. Okay, so what is the graph of this? What is the graph of f of x is equal to x plus 3? Well, it's just a linear function. Here's the y-intercept. Here's the x-intercept. And here's the thing, when you plug in, whenever you would have 3, you can't plug 3 into this. Okay, so when you go to 3, when you were to look at the graph, there would be a hole in the graph at x is equal to 3. And then it would look just like this. And suppose you don't, you're just like, I don't know, I'm not sure I believe you, Matt. Let me just show you this. Let me load up the graphing calculator here. And if I were to even, I'm just going to reset my calculator real quick. If I were to even, sketch this, plug this into the graphing calculator, right? So you get x squared minus 9 divided by. If you were to look at the graph, look, the graph is the straight line. So the only thing that I have here that you're not going to see on your graphing calculators, there is going to be the hole in the graph. But look, you can see this function is just a straight line. So now, what happens to the function f of x as x approaches x is equal to 3? Okay? So this is going to say, look, what happens to the function when you take x and you look at it and say, what happens to the function as x approaches 3? Where does it look like the function is going? And look, as x goes to 3 from below, okay, where does it look like this graph is going? It looks like it's going to 6. And it's the same thing. If you look at the function as x goes to 3 from above, so from the right, where does it look like this graph is going? Even though there's a hole in here, in the hole in the graph, okay, because the graph is the function is undefined for when x is equal to 3, it still looks like, so as x approaches 3, as x is approaching 3, not exactly 3, but as it's approaching it, where does it look like the function is going? And it looks like it's going towards 6. This concept is called a limit. And it would look like this. You write it like this. The limit, and I'm going to have the formal definition on the next page. As x goes to 3 of f of x, well, what does it look like? It looks like it's going towards 6. All right, so it's the limit of this f of x as x goes to 3, and it looks like, so as x goes to 3 from below, it looks like the graph is going towards the value 6, and as x goes to 3 from above, it looks like the graph is going to 6. All right, so that's the basic kind of concept of a limit. Where does it look like the graph is going? So let me give you the formal definition. So the formal definition of a limit, or how we'll write it in this class, as x approaches a, so it could be any real number, okay, the limit of f of x is equal to L, okay, is written as the following. The limit as x goes to a of our function f of x is equal to some number L. Okay, and the way this works, if all values of f of x are close to L, okay, this value L, for values of x that are sufficiently close but not necessarily equal to a, the limit L, if it exists, must be a unique real number. So what this means, okay, and I'm going to go back to the previous slide here. When you're evaluating a limit, you look at values really, really close, okay, to this a. So like, look, I'm looking as values get really, really close here. Like, what happens as I get close to x is equal to 3? Well, where does it look like the graph is converging? So even though there's a hole in the graph here, okay, we can still say, look, it looks like the values are going towards 6. All right, so what I want to do now is I want to show you some methods for how you find or how you evaluate a limit. The first one is with a table of values numerically. The second way is visually, graphically. That's this lecture here. And then what I'm going to show you in a follow-up lecture in the next section, we're going to talk about how you solve them analytically. Okay. So here's the first way, okay? How you solve it with the table of values. So I want to look at this problem again here, okay? So I want to find the limit as x goes to 3 of f of x. So I want to find the limit as x goes to 3 of that x squared minus 9 divided by x minus 3, okay? So here's this number I'm looking for. I want to find this limit. Like, what is this limit equal to? So going back to our definition, you look at values that are sufficiently close. All right. So you'll notice I have a table here that has 3 spots. Well, look, sufficiently close is really a number like 2.999, like really, really close to 3. And let me back it out just a little bit further. So I'm going to pick 2.9, 2.99, 2.999, okay? And then, so that's going to be values from below, like really close to 3, like 2.9, 2.99, 2.99. And then I have to pick values that are just above 3 as well. So I'll pick 3.001, 3.01, and 3.1. So like as you get closer and closer to 3, like 2.99 and 3.001 are really close to 3, okay? So what you're going to do is you're literally going to take these values and you're going to plug them into your function. So f of 2.9, you're literally going to take 2.9 squared minus 9 divided by 2.9 minus 3. All right, so watch this. So I'm going to grab my calculator here. And watch what happens when I plug this in, okay? So I get 2.9 squared minus 9 divided by 2.9 minus 3. Look at this, I got 5.9. And I'm just going to save a little bit of time here. If you plug this into your function, literally, so if you go f of 2.99, you would end up getting 5.99. If you were to plug 2.9999 into this, you would end up getting 5.999. So like, look, as x is getting closer and closer to 3, right? So as x is going to 3, what value does it look like f of x is going towards? 5.9, 5.99, 5.999. Like, it's obvious. It looks like it's going towards 6. If you were to do the same thing above here, and I'll save some time in the video, like if you were to plug 3.001 into this function here, you would get 6.001. And it's the same thing on the other side. If you were to plug these in, you'd get the following values. So look, your table of values saying, look, as x is going to 3 from below, so values that are just below, looks like it's going towards 6. And as x goes to 3 from above, so values just slightly above it, look, it looks like it's going to converge to 6. Which is literally exactly what you saw when you looked at this graph here. All right, so let's do another one, okay? We'll do one here that's that we don't know what the graph looks like, okay? So here's the second one, so using this same type of concept here. Let's find the limit as x goes to 4, okay, of x minus 4 divided by x squared minus 5x plus 4. And what's really interesting, is if you just take 4 and you plug it into this, okay, like if our function f of x is equal to x minus 4 all over x squared minus 5x plus 4, if you look at what f of 4 is equal to, you get 0 over 0, which is that indeterminate form, okay? So the function is undefined. It's undefined for x is equal to 4, okay? But does the limit exist? Okay. So can I evaluate this limit? Like, is this limit equal to something? Well, again, so let's pick values that are pretty close to 4. Okay, so you can see I'll pick 3.999, I'll pick 3.99, and I'll pick 3.9, and it's the same thing. I'll pick values just above it, right? So 4.001, 4.01, and 4.1. And I'm going to look what happens as I get closer and closer to 4 from below and closer to 4 from just values just above. So look, I'll plug 3.9 in here, and let's see what happens, okay? So you're going to get 3.9 minus 4 divided by 3.9 squared minus 5 times 3.9 plus 4. So look what you got, 0.3448, okay? All right. So I worked these out ahead of time. So if you were to plug all the rest of these values in, this is what you would get. If you were to plug 3.99 in, you get 3.3344. Then you would get 0.3334. If you were to plug 4.001 in, you should see what's going on here. I think it's 0.033. I think it's 2. I'm sorry. So the next one would be 0.3322, and then finally 0.3226. Okay. So look what's happening, right? Where does it look like as x goes to 4 from below? Does this look like it's going towards 0.33333 repeating? And the same thing on this side. As you go this way, where does it look like it's going, right? Doesn't it look like it's going to 0.33333 repeating? Okay. 0.333 repeating is just 1/3. So again, what you're seeing here, even though the function is undefined when you plug in x is equal to 4, okay, the limit can still exist. So just an interesting concept. Okay, so even though it does not exist, the limit as x goes to 4 of f of x still existed. Now, I don't want you to think that that will always work. All right, that's not always the case. So what you're seeing here is as you go from below and as you go from above, okay, you have to look like you're going to the same place. Like going back here, just looking at the graph. As x goes to 3 from below, and as x goes to 3 from above, they're going towards the same place. Okay, they're both going towards this value 6. All right, let's do a trig one. Okay, So let's evaluate the following here. Okay, the limit as x goes to 0 of sine of x over x. And again, okay, if you let f of x be sine of x over x, f of 0, if you were to just plug this in, sine of 0 divided by 0, you would get 0 over 0, right? So again, it's undefined. All right? But this is what I call the indeterminate form, so that generally means the limit's going to exist. So I want to find as x goes to 0. So I'm going to pick some values just below 0. So I'll start with negative 0.1, negative 0.01, negative 0.001, and then values just above 0. So 0.1, 0.01, 0.001. All right, so I'll plug in this first one here. I'll plug this into my calculator so you can see it. So I'm getting sine of negative 0.1 divided by negative 0.1. Look what I got, 0.9983. And if you were to plug the rest of these in your calculator, literally this is what you would see. So it'd be like, you can obviously see, look, as x is getting closer and closer to 0, it looks like the values are going towards 1. As x is getting closer and closer to 0 from above, it looks like x is going to 1. So this limit is indeed 1 here. Okay, so using a table of values, just as a rehash, you need to pick values slightly above the value in the limit here, some values slightly below, and just plug them in and see if it looks like they're converging to the same value. Okay. Sometimes graphically is a little bit easier. Okay, so when you look at the graph, that can be an easier way to evaluate a limit. Okay, so consider this function right here on the right, f of x. Okay, its graph is shown here. So let's find each of the following. Okay, so first, let me just find f of 1. So look. This black line, this black dot here is the function. So when f is equal to 1, here's the dot, the function is equal to 2. All right, now, so here's the thing. This is interesting. The function exists at 1. But look at the limit as x goes to 1. Look, as x goes to 1 from below, so as you're getting closer and closer to 1, look where the graph looks like it's going. It looks like it's going to this value. When you look at as x goes to 1 from below, it looks like it's going to this value. So notice that from below it looks like it's going here, and from above it looks like it's going here. So they're not what we call the one-sided limits are not going to the same place. So this is a limit that whenever you'll see this notation DNE, it means does not exist. And that's okay. Sometimes limits don't exist. Like just the one-sided limits don't go to the same place. All right, that's okay. So notice here the function exists, but the limit doesn't, which was really interesting because in the previous examples what was going on was you would see that the function didn't exist, but the limit did. So this was backwards. Now let's try this, f of 4. So when you go to 4, look, there's a hole in the graph. Okay, so it's undefined. Okay. But when you look at the limit as x goes to 4, well, look, when x goes to 4 from below, where does it look like the graph is going? It looks like it's going to the value 2. When you look at it where it's going from above, it looks like it's also going to 2. Not exactly at 4, but where does it look where it's going? And it looks like it's going to 2. So that's a case where you have to pay real close attention to the graph and look at the one-sided limits. Look where they're going. All right, here's another crazy one here. Okay, so there's a lot going on here. All right, so consider this function here. Okay, and I want to find all of these things. All these things. All right, so first off, let's find f of negative 2, excuse me. Well, I go to negative 2, and notice you see there's a vertical asymptote. Okay, so you know what? It's undefined there. All right, the graph doesn't exist there. It's a vertical asymptote. And then look, when you look at the limit as x goes to -2. Well, when you go from when you look at the graph, you look at the function when it goes to -2 from below, it looks like it's shooting down towards -infinity. And then when you look at it from above, so values just above -2, looks like it's going to positive infinity. So opposite directions. So this does not exist. This limit does not exist. There's no value for it. So look here, f of 0. Okay, here's 0. When I go look at the function value, there's a hole in the graph. So here it's undefined. Now look here. Okay, limit as x goes to 0. Well, look, when you look at where as x goes to 0 from below, so you're getting closer and closer here, it looks like it's going towards, I don't know, this looks like 1/2. But when you look as x goes to 0 from above, it's going up towards 4. So the one-sided limits don't go to the same place. So this limit does not exist, DNE. All right, let's look at f of 2. Well, go to 2. There's a hole in the graph. Undefined. But look, the limit as x goes to 2. Well, as x goes to 2, looks like the graph is pointing towards this value here, which looks like 1/2. And as x goes to 2 from above, it looks like, look, the two one-sided limits, it looks like they're going to the same place. Like the two arrows are pointing to the same value. And that value is 1/2. Because here's 1, so this is roughly 1/2. Now look here. F of 4, you go to 4. Looks like this is just 2. And now this is interesting. Limit as x goes to 4 of f of x. So look what's happening here. As x goes to 4 from below, looks like the graph is shooting up towards infinity, positive infinity. As x goes to 4 from above, it looks like the same thing. It looks like it's shooting up towards infinity. So there's a common mistake here to say, oh, well, it looks like they're both going to infinity. This is equal to infinity. We still say this does not exist, okay? Infinity is not a number, right? It represents increasing without bound. So it does not exist. But here's the thing. You can still describe the behavior, okay? So you can still say it does go to infinity. But I don't want you to think that that means it's equal to infinity. We would still say it does not exist. Okay. Let's try this one. Okay. I want to show that the limit as x goes to 0 of the absolute value of x divided by x does not exist. Okay. And the easiest way to do this would be to sketch the graph of, when you sketch the graph of this function, absolute value of x over x. Well, look, you can't plug in 0, first off, okay? When you plug in 0, you get 0 divided by 0, that's undefined. Well, when you plug in any positive number, the absolute value of a positive number is just a positive number, right? So this would just be x divided by x. It would just be 1. So for any positive number, there'd be a hole at 0. For any positive number, it would just be 1. Now look at this, all right? If you look at when x is less than 0, okay, you'd get positive x because you'd have an absolute value, positive x divided by negative x. So you would just get -1. And look, the limit as x goes to 0, it looks like it's going towards -1 from below. And as x goes to 0 from above, it looks like it's going towards 1. They're not going to the same place. So the one-sided limits do not agree. Thus, this limit as x goes to 0, the absolute value of x over x, does not exist. Okay. So sometimes just very simply like looking at the graph can do it for you. All right, let's try some other, this one right here. Okay, let's find the limit if it exists of this. Okay, the limit as x goes to 0 of cosine of x over x. Now here's what's interesting, right? If you do this, have f of x be cosine of x over x, and you plug in 0, you get cosine of 0 over 0, which is 1 over 0. So notice that you don't get the 0 over 0, all right? You don't. This is not that indeterminate form I was talking about. So it's still undefined. So when you look at the graph, here's what's going to happen. It's going to start oscillating. As you get closer and closer to 0, it's going to go up between 1 and -1. It's going to go, and then when you go this way, it's going to keep oscillating and oscillating and oscillating and oscillating. Like even if I plug this into my graphing calculator, you know, it's harder to see it like this. So let me like zoom in. You can't really see it on the graphing calculator here. But if you were to just look at the graph like this, you would notice that it just goes oscillate between -1 and 1. You get really, 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 really close. So it doesn't look like it ever converges. Okay, so when a graph oscillates like this, goes up and down, up and down, up and down, up and down on both sides, this limit does not exist. Okay. Let's do these now. These are fun. Okay. So let's sketch a graph of a function f that satisfies the following conditions. And note there may be many correct answers here. Okay, this will be our last slide. These are a little bit fun. Okay. So here's the first one. And there's many different ways you could do this. All right. So the first one says f of 0 is undefined. But listen to this. But the limit, okay, the limit as x goes to 0 is equal to 4. So what that means, it's undefined, okay, but the limit exists. So there has to be a hole in here, okay? And then the function on both sides have to come up really, really close to it. Okay, now here's the next thing. F of 2 has to be equal to 6, okay? Oops, sorry about that. F of 2 has to be equal to 6, so it has to be that right there. But the limit as x goes to 2 has to be equal to 3. Okay, so the limit is going to be equal to a different value. So I'm going to put a hole in here. And now you tell me if, as I sketch this, this works. Well, look here. F of 0 is undefined. There's a hole in it. The limit as x goes to 0. Well, look, the limit looks like it's going towards 4. F of 2 is equal to 6, but the limit as x goes to 2, looks like it's going towards 3. All right, so now here's some other ones, okay? The f of -2, so -2 is 0, okay? F of 2 is also 0, okay, so I know that those have to be two points on it. The limit as x goes to -2 has to be equal to 0. That's okay, so that's great. So that means the graph has to go through this. But then the limit, okay, as x goes to 2 of f of x does not exist, okay? So there's a bunch of ways you could do this, all right? So here, I'm going to have this go here, but then up here, I'm going to have a hole. And watch what I'm going to do. I'm going to have the graph look like this. And let's see how this works. F of -2 is 0. Boom. F of 2 is 0. Got it. Limit as x goes to -2. Yep, it does go to 0. And look, the limit as x goes to 2, it does not exist, right? Because from below it goes to this value, but from above it looks like it's going to 4. All right, class. There was a lot to digest here. So I encourage you to watch the video numerous times to have it make sense for you. And as always, I'm here for any questions you might have.